2.2 Transmission of information. In digital communications, a signal is defined as a code used to convey specific content or information. The information embedded within a signal manifests as characteristic variations in its properties. Consider human speech. It can be modeled as a waveform, which can be analyzed through its frequency, amplitude, and phase, the latter of which determines the timbre, or tone color of the voice. Consequently, human speech conveys information through continuous changes in these three elements. For instance, in the sentence "I go to school every morning," each syllable possesses distinct acoustic characteristics, resulting in unique voice signals. This principle applies to visual information as well. A painting on a canvas consists of various colors. Since each area painted with a different hue holds unique color information, the canvas can be represented as a color signal. Much like each syllable in speech contains distinct data, each region of a canvas possesses unique characteristics that constitute a signal. In image signal processing, the unit area that represents these different color details is called a pixel. Mapping source information, such as a voice or a painting, into electrical signals is the fundamental starting point of signal processing. Information cannot exist without change. Silence lasting for an hour or a sound maintained at a constant pitch and volume carries no information. Human speech is informative precisely because it changes over time. Mapping information to an electrical signal means correlating the factors of change in the source to corresponding factors in the electrical signal. Specifically, the pitch, volume, and timbre of a voice are represented by the frequency, amplitude, and phase of its waveform. Converting speech into an electrical signal involves mapping these vocal variations onto the fluctuations of an electric current, which are then mirrored in the signal's frequency, amplitude, and phase. Ultimately, converting a voice into an electrical signal means transforming the temporal patterns of vocal change into corresponding patterns of electrical change. While a human voice cannot travel physically from Seoul to Busan, a voice converted into an electrical signal can. However, in the general process of transmission and reception, signals can be lost or distorted while traveling through the channel. Therefore, countermeasures are required to prevent the loss or distortion of transmitted information. This necessitates analyzing the signal and finding transmission methods suited to the specific conditions of the channel. In the following sections, we will explore signal characteristics and transmission methods, with a particular focus on spread spectrum communications. In this section, mathematical formulas are kept to the minimum necessary for conceptual explanation, though they may appear more frequently than in other parts. These equations are used not to focus on the step-by-step mathematical derivation, but rather to borrow established principles to clarify core concepts. Throughout this book, any formulas presented are intended to be concise expressions of abstract concepts, offering new or alternative perspectives, and serving as the systematic conclusion of logical reasoning. 2.2 1 Fourier transform. Fourier, a 16th-century French mathematician, proposed that any periodic signal consists of a fundamental frequency signal inherent to it, and a sum of its harmonics. Here, the signal with the fundamental frequency is called the fundamental signal, and signals with frequencies that are integer multiples of that fundamental frequency are known as harmonics. This is the core principle of the Fourier series. 5 centuries later, the Fourier series serves as the foundation for the Fourier transform, a vital theory in modern signal analysis. The Fourier transform converts a signal's representation from the time domain to the frequency domain. There are two ways to represent a signal: by its shape over time, or by its shape across frequencies. Generally, these two perspectives show different aspects of the same signal. It is much like how the same building looks different when viewed from the front versus from a bird's eye view. Through the Fourier transform, we can see another dimension of a signal. Just as a front elevation reveals the number and shape of windows while a plan view from above shows a hidden rooftop garden, the time domain perspective allows us to observe temporal trends, while the frequency domain perspective reveals frequency-specific characteristics. When observing a signal through an oscilloscope, we see it changing over time. Conversely, through a spectrum analyzer, we can observe the signal's variations across frequencies. Equation 2.4 shows the complex form of the Fourier series for a periodic signal appearing on the time axis. The term e to the jn omega naught t in equation 2.4 is the exponential representation of sinusoidal signals like sine and cosine. Therefore, Fn represents the magnitude of the harmonic signals, those with frequencies n omega 0, which are integer multiples of the fundamental frequency. This shows the specific magnitude of each frequency component within the signal Ft. In this regard, Fn represents the frequency characteristics obtained by observing the signal from a frequency perspective. In other words, Fn is the signal Ft, as seen in the frequency domain. A defining characteristic of a periodic signal is that its waveform repeats continuously over a fixed time interval, known as the period. Consequently, observing just a single period is sufficient to understand the characteristics of the entire signal. For this reason, Fn is defined as the cross within one period, and the complex exponentially to the jn omega naught t. This relationship is expressed in equation 2.5. Based on this result, the original signal Ft can also be reconstructed as shown in equation 2.6. A signal that possesses a period is called a periodic signal. However, to definitively confirm a signal's periodicity, one would theoretically need to observe and verify it over an infinite duration. Since observing a signal for an infinite amount of time is impossible in practice, strictly speaking, true periodic signals do not exist in the real world. Rather, it is more accurate to say that in reality, there are signals that can be approximated as periodic within a specific time interval, or under certain conditions. The approximated signals referred to here encompass virtually all general signals we handle in a laboratory environment. Therefore, the Fourier transform should be understood as the application of the Fourier series to the practical, general signals we encounter in the real world. The Fourier series carries a mathematical significance as an interpretation of periodic signals, and should be regarded as a conceptual framework. Therefore, we need the Fourier transform to serve as a practical and effective tool for analyzing signals. In this regard, the Fourier transform can be assumed to be a Fourier series applied to non-periodic signals. Since the period of a non-periodic signal is infinite, the finite value n omega 0 becomes the differential d omega, approaching 0. As a result, the summation sigma, which adds discrete values, is replaced by the integral symbol, which adds continuous values. Accordingly, the summation interval from t0 to t0 changes to an integration interval from minus infinity to plus infinity. Furthermore, other parameters change as follows. Furthermore, e to the jn omega naught t and e to the minus jn omega naught t must be replaced with e to the j omega t and e to the minus j omega t, respectively. Overall, as discrete values are transformed into continuous values, equation 2.6 is modified into equation 2.7. From this, we can derive the inverse Fourier transform formula, where the frequency function φ is expressed as Ft, and the Fourier transform formula, where the time is represented as the frequency. Equations 2.5 and 2.6 have been transformed into equations 2.7 and 2.8, respectively. Here, equation 2.7 is referred to as the inverse Fourier transform, while equation 2.8 is called the Fourier transform. To clarify exactly what the result of the Fourier transform represents, let us compare the Fourier series of a periodic rectangular pulse train with the Fourier transform of a non-periodic rectangular pulse. A periodic rectangular wave has an amplitude of it during the interval from t2 to t2, with a period of t. When we calculate Fn using equation 2.5 for this signal, we obtain equation 2.9 as follows. Using figure 2.5, let us compare the Fourier transforms of a periodic rectangular pulse train and a non-periodic rectangular pulse that appears only once. As shown in figure 2.5b, Fn appears only at the fundamental frequency and its integer harmonics. Thus, the Fn values are distributed sequentially at discrete intervals of the fundamental frequency. Recalling our previous discussion, this was the very definition of the Fourier series. Now, to investigate the frequency domain characteristics of the non-periodic rectangular pulse shown in Figure 2-5c, we will perform a Fourier transform. First, the rectangular pulse to be transformed is as illustrated in Figure 2-5c. Completely isolated, possessing significant values only within a specific time interval and remaining zero elsewhere. By applying this signal to equation 228, the Fourier transform formula, we obtain the result shown in equation 210. Whether the rectangular pulse is periodic or non-periodic, the magnitude of its frequency components spreads infinitely in the form of a sinus function centered at the origin. In the case of periodic functions, the frequency components appear at discrete intervals of the fundamental frequency. In contrast, for non-periodic functions where the fundamental frequency can be thought of as non-existent or infinitely small, the result appears as a continuous function representing magnitudes across all frequency components. Ultimately, we can see that the result obtained through the Fourier transform represents the magnitude distribution of frequency components. A non-periodic rectangular pulse in the time domain exhibits an amplitude of a only within the interval from t2 to t2, while no signal exists in any other time period. In the frequency domain, this pulse is represented as a sinus function that spreads across an infinite frequency range. Figure 2-7 illustrates how certain critical values of the sinus function in the frequency domain relate to the width of the rectangular pulse in the time domain. Specifically, Figure 2-7 displays the frequency characteristics of three rectangular pulses, each with a different width. The characteristic feature here is that the width of the rectangular pulse in the time domain and the distance to the zero crossing points of the sinus function in the frequency domain are inversely proportional. In other words, as the width of the rectangular pulse in the time domain increases, the zero crossing points in the frequency domain become smaller, or move closer to the origin. 2.2 FZC bandwidth. What, then, is the significance of the zero crossing points in a sinus function? To understand this, let us analyze the power density of a rectangular pulse by frequency. Whether we refer to the time domain or the frequency domain, these are merely different perspectives from which we observe the same signal. Therefore, the time domain signal and the frequency domain signal are not distinct entities. The energy of a rectangular pulse remains the same whether it is measured in the time domain or the frequency domain. Consequently, the power of a rectangular pulse is at square. This is equal to the area under the sinus function across the infinite frequency range, which is calculated through integration. Meanwhile, Figure 2-8 illustrates the relationship between the power spectrum representation of a rectangular pulse and the transmission bandwidth. When the integration range is limited to the first zero crossing point, it can be seen that this value accounts for approximately 90% of the total power. In summary, to transmit a rectangular pulse in its perfect, original shape, all frequency components spanning out to infinity must be transmitted. This leads to an unrealistic situation where an infinite bandwidth is required. However, if we transmit only the signal components up to the first zero crossing point, we are effectively transmitting about 90% of the total signal. This allows us to deliver a signal that is nearly identical to the original. It is impossible to transmit a rectangular pulse in its perfect shape. For instance, to perfectly transmit a rectangular pulse that rises and falls very sharply at t(p)(m)(t2) and maintains a flat amplitude during the interval from t2 to t2, one must transmit all the infinite frequency components contained within the pulse. In other words, an infinite transmission bandwidth is required. Since we must use an infinite bandwidth, we instead establish a limited bandwidth by giving up some of the harmonics. We can omit these components, that is, perform an approximation, because our goal in transmitting a rectangular pulse is not to preserve its unique shape, but to convey the meaning it represents, such as A1 or A0. This is because what we transmit using the transmission bandwidth is the delivery of 1 or 0. Therefore, to interpret the information of the rectangular pulse at the receiver, we set the transmission band to include the harmonics that contain most of the signal components, corresponding to about 90%, while excluding the harmonics that are safe to ignore. 2.3 For transmission bandwidth for digital signal. Since more than 90% of the power of a square wave is concentrated within the bandwidth up to the FZCP, it can be understood as a measure of the transmission bandwidth of a wave. For this reason, the transmission bandwidth of a digital signal can be said to be equal to the pulse width, that is, the pulse transmission rate. To this, the frequency error range of the oscillator will be added, and depending on whether the transmitted data is sent according to the spectral efficiency of the modulator, its bandwidth can be defined as shown in equation 211, where B represents the bandwidth, RD is the data rate, eta is the spectral efficiency of the modulator, and delta F denotes the variation range of the transmission frequency. The spectral efficiency of the modulator indicates how many bits of information are contained within a single modulation symbol. It is 1 for BPSK and 2 for QPSK. That is, it can be seen that one modulation symbol of QPSK consists of 2 bits, which are 00, 01, 10, and 11. Therefore, a 2-bit QPSK symbol can transmit for different types of information. In short, we have confirmed that a signal with a narrow square wave pulse width characterized by extreme signal transitions or a signal with a high transmission rate must be transmitted over a wide bandwidth. Furthermore, it can be understood that data transmitted over a wide bandwidth is data that possesses a very high data rate. Based on our conclusions so far, we have established that high-speed signals are transmitted over a wide bandwidth, and that such signals possess extremely narrow pulse widths. Consequently, we can understand that spreading a signal means transmitting it over a bandwidth wider than what is strictly required to represent the original information. In other words, it involves making the pulse width of the digital information, bits, even narrower. That is correct. To spread a signal is to transform the signal to be spread into an even faster signal. The method for achieving this is to multiply or modulate the information signal with a signal that is much faster. In this process, the signal used for multiplication or modulation is called the spreading signal, and this spreading signal is significantly faster than the original information signal. Then, what does it mean to transmit at an even higher speed? This implies that there is a perfectly suited transmission bandwidth for transmitting specific information. In other words, while one could simply transmit at that optimally suited rate, transmitting faster than that is precisely what it means to communicate by spreading the frequency bandwidth. 2.2. For Nyquist bandwidth, information collected in analog form is converted into a digital signal through sampling, which periodically extracts samples of the signal only during specific time intervals. This signal is then modeled as a square wave, which is a rectangular-shaped pulse signal. An analog signal appearing in a continuous flow of time becomes a discrete time signal when sampled at regular intervals. This signal is then quantized into codes that represent specific values, ultimately becoming a digital signal. Then, what is the basis for the argument that a discrete signal, which appears discontinuously in a time series, is equivalent to an analog signal, which appears continuously? An analog signal sometimes contains information that is completely unnecessary, or can be sufficiently ignored. Such elements are directly linked to the continuity of the analog signal, the fact that it appears incessantly. In other words, if we only wish to obtain the specific information we need from an analog signal, we can forego its continuity. This concept is the most fundamental idea behind sampling. Therefore, if one chooses to give up continuity and obtain only limited components, one can argue that the analog signal and the discrete signal are identical. This claim is based on rational judgment and is predicated on a valid assumption. Such sampling is necessary because we do not desire all information, but only the essential information for communication. A representative example is knocking on a restroom door. We do so simply to check whether someone is inside, not to gather detailed information about the interior, such as the color of the walls or the shape of the toilet. What we must now consider is the sampling interval used to convert an analog signal into a discrete signal. In other words, we are seeking the answer to exactly how long that constant time interval should be. Let's consider sampling S1 ton, a sine wave oscillating at a frequency of 100 Hz every 10 milliseconds. If you sample S1 ton at a sampling frequency of 100 Hz, the result captures values over one period of S1 ton. Those values will be either positive or negative. However, a sine wave changes to a positive value for half of its period, and a negative value for the remaining half. More accurately, the values during the first half period become different values during the second half period within a single cycle. Therefore, by sampling S1 ton at 10 to fully understand the characteristics of the sine wave S1 ton, it must be sampled more rapidly at a sampling frequency of 200 Hz, which is at least a 5 millisecond interval. That is, by sampling S1 ton at 10 milliseconds, the first sample captures a value from the first half and the next sample captures a value from the second half period. Now, through sampling, all the characteristic values representing S1 ton have been extracted. Consequently, to sample the information of a signal, it must be sampled at a frequency twice as fast as the frequency of that signal. However, most signals we encounter in reality are not so-called single-tone signals that possess only a single frequency. In this regard, we must consider the sampling frequency for signals where multiple frequencies are mixed together. Consider a signal MT, which is a combination of three sine waves, S2 tons and S3 tons, with frequencies of 100 Hz, 200 Hz, and 300 Hz, respectively. Suppose we sample this combined signal MT at a sampling frequency of 400 Hz. In this case, the 400 Hz sampling frequency can capture all the characteristics of the 100 Hz and 200 Hz signals. However, it cannot accurately detect the changes in the 300 Hz sine wave. Therefore, to sample the information of the 300 Hz sine wave included in MT, we must sample at 600 Hz, which is twice the highest frequency component, 300 Hz, present in the signal. Sampling at a frequency twice as high as the maximum frequency component means sampling the signal twice as fast as the fastest changing component. Then, what is the value of this highest frequency component in an analog signal? This value depends on the degree of information we wish to obtain from the analog signal. For instance, an analog signal like a human voice likely contains countless frequency components extending toward infinity. However, for a telephone conversation, we typically require frequency components only up to 4 kHz. Of course, one could choose to include even higher frequency components, such as 8 kHz, or beyond. In other words, sampling a signal at a specific sampling frequency implies band limiting the signal to half of that sampling frequency. Furthermore, this also means performing band limit filtering. The explanation provided so far has been an intuitive interpretation of the well-known sampling theorem. Now, let us examine the physical meaning of sampling through a more analytical approach. A general signal, FD, consists of a fundamental frequency signal, and the sum of harmonics that have frequencies as integer multiples of that fundamental frequency. The resulting signal, FSD, which is obtained by extracting FD, using impulses at regular time intervals, can be written as shown in equation T12. To identify the characteristics of equation T12 in the frequency domain, we perform a Fourier transform. The Fourier transform of equation T12 involves the convolution of the Fourier and the impulse train, del tot. When the multiplication operator is Fourier transformed, it manifests as a convolution, that is to say, multiplication in the time domain is convolution in the frequency domain. This is the very definition of the convolution operator. As a result, the frequency characteristics of the sampled signal are expressed by equation T13. The signal resulting from sampling FD shows that the original spectrum of FD appears repeatedly at every integer multiple of the sampling frequency, omega edge, of the impulse train, del tot. Of course, the version of FD that appears here does not include all the signal components of the original analog signal, but only those valid within a bandwidth equal to half the sampling frequency. From this, we can see that the multiplication operation shown in equation T12 is, systemically, a filtering process. This confirms the earlier point that the sampling process is, in fact, a band-limiting filtering process. Furthermore, since we have established that sampling is a band-limiting process, it follows that there is certain information being restricted or limited through sampling. Then, what is the information we lose or omit during the sampling process? These, too, would be the elements we judged to be ignorable, or negligible. If we lose a portion of information through sampling, we cannot perform it indiscriminately. Therefore, by adjusting the sampling frequency, we must control the amount of information that is omitted. In other words, we must determine a sampling frequency fast enough to ensure no essential information is missed. For example, if the information required for general conversation is mostly concentrated within a 4 kHz range, we can use a sampling frequency of 8 kHz for voice calls. For better sound quality, we can increase the sampling frequency. For instance, CDs used for recording music have a sampling frequency of 44.1 kHz, which is much higher than that of voice calls. In figure 2-9, the time interval t, which is both the repetition period of the impulse and the sampling period, is called the Nyquist interval. For example, more than 90% of the information necessary for its representation. Furthermore, to sample a signal transmitted over the Nyquist bandwidth, a sampling frequency of twice the Nyquist frequency is required. One thing to note here is that the Nyquist frequency band is the bandwidth intended for transmitting the band-limited information obtained by sampling the original signal. It is not a bandwidth meant for transmitting all the information of the original signal. 2.2.5 The meaning of spread spectrum. To ensure the transmission of reliable information, an information signal is transmitted at the Nyquist time interval. Transmitting at the Nyquist time interval means that the signal is being sent using the Nyquist bandwidth. If a bandwidth narrower than this is used to transmit information, the receiving end will receive a distorted or warped signal. Conversely, if a wider bandwidth is used, the signal will not be distorted, but it would be a waste of bandwidth. This is similar to paying 2001 for an item that costs only 1001. At first glance, the spread spectrum communication method appears to waste bandwidth because it communicates over a broader frequency range than is strictly necessary. However, paying 2001 for a 1001 item is not always a waste of money. While it might be considered a waste from a purely economic standpoint, it could also be a deliberate choice to gain an advantage in another area. Although spread spectrum may seem to waste spectrum in terms of effective division and usage, it offers different benefits from another perspective. To spread a signal for transmission, the information signal must be modulated by a spreading signal, which is understood as a very high-speed signal. Here, modulating the information signal means that, in addition to multiplying the information signal by a carrier wave, the information signal is also multiplied by the spreading signal. In communication engineering, the modulation process is mathematically equivalent to multiplication. However, the specific form of this very fast signal is not strictly predefined. For instance, while the shape of the information signal is determined by the data being transmitted, the spreading signal having no specific information of its own does not have a predetermined shape. The spreading signal is defined only by its speed to fulfill its function of spreading the information signal. In other words, the direct characteristic of a spreading signal lies not in its shape, but in its speed. Deciding on a spreading signal is akin to dressing a naked person to give them a concrete appearance. To determine the entity of that signal, we must focus on the requirement that the spreading signal must be a very high-speed signal. Let us consider the characteristics that a signal used for spreading should possess. Since a spreading signal occupies a much wider bandwidth than the information data, it has a significantly higher bit rate. This means the spreading signal changes much faster than the information, and must exhibit much more diverse variations. We predict future occurrences by reviewing past events or trends. When we can observe many past situations, that is, if those situations occurred frequently, prediction becomes easier and more accurate. In other words, the degree of predictability is determined by the frequency or the length of the period in which situations occur. A shorter repetition period makes prediction easier, while a longer period makes it more difficult. When a situation occurs that is difficult or impossible to predict, we say it happens randomly. The requirement that a spreading signal must be much faster than the information signal and possess diverse variations implies that its repetition period must be very long, and its changes must occur randomly. Furthermore, despite being a high-speed signal, it must be easily acquirable by the receiver and possess randomness similar to information data. To satisfy these characteristics, the spreading signal is shaped as a PN code, also known as a pseudo-noise signal. The p encode patterns for spread spectrum communication are generated using linear filters, where delay taps that deliver input bits with a 1 clock delay are connected in long sequences. We will study this in detail at the end of this chapter. In the following section, we will explore the specific gains that can be achieved through spread spectrum communication.